Okay, so you only need linear algebra. But my question is, how well do we really understand linear algebra? Yeah. And there are certain parts of linear algebra that we do not understand very well, in my opinion, and that is what I'm going to talk about. So eventually, I want to talk about what I call the Hodge-Riemann relations. But before going that, as a sort of a preliminary, I'll talk about another statement in linear algebra that I'll just call hard Lefschetz. So there is a well-known theorem that goes under the name of Lefschetz in complex geometry. But one of the things we have noticed over the years is that the same form of the statement not only holds in the context of complex projective geometry that Lefschetz was originally interested in, but also in numerous other cases. And I'm going to talk about one variation of the classical hard Lefschetz theorem in the context of linear algebra, which is already quite non-trivial and tells us what part of linear algebra that we do not understand very well. So let's start from, say, a finite set. So I'm going to call E a finite subset of a plane. Say a projective plane if you want, or simply a plane in whatever naive sense you have. And let's ask ourselves, how many lines does E determine? So what do I mean by this? So suppose I have 4 points in the plane, say in general position. Those are my 4 points. And what I'm going to do is connect every pair of points by a line. So here's my one line, 2, and the third line, 4, 5, 6. And I'm going to say that this finite set of 4 points determines 6 lines. Of course, I can start with another set of 4 points and arrive at a different number. Suppose I have 4 points, now in slightly more special position. Say 3 of them collinear. And then something changes. If I produce the same picture here, by connecting every pair of points by a line, I get 1, 2, 3, 4, and no more. So in this case, I would say the set of 4 points in special position determines 4 lines. And if I increase the number of points, you can create even more interesting figures. So here's my favorite one, where you introduce coordinate to your projective plane and pick all 7 points with 0, 1 coordinates. So here's my 5, 6, and 7 points. And the coordinates are like 1, 0, 0, 0, 1, 0, and 1, 1, 1, etc. And then if you produce the lines, then you get a picture like this, where 7 points determines 9 lines. You can do something interesting with this particular configuration of 0, 1 vectors, or 0, 1 points. The picture I have drawn here is implicitly using the fact that the field I'm using is real numbers, or is rational numbers. So instead, let's take the characteristic of the field that I'm using to coordinatize my plane and take the characteristic P of the base field approach to 2. I can do that because all the coordinates are 0, 1, and I can ask the same question over every field. So long as my characteristic is not 2, you will see the essentially same picture, 7 points terminating 9 lines. But at the limit where your P becomes equal to 2, where you pick all 7 rational points in the projected plane over the finite field with 2 elements, then you will notice that at the limit, the 3 points become collinear, destroying 3 lines and creating 1 new line. So this is the famous picture of the so-called Fano plane, where 7 points determine 7 lines. But in any case, no matter what field over which you're working with, you'll always see that this number on the right is larger than, at least as large as the number of points. So that observation is a theorem of De Broglie and Erdős. One of the earliest theorems in this field of combinatorial geometry, which explains what we have observed in these examples. So for any set, finite set of points E in a plane, E determines at least cardinality E many lines, with one obvious exception. Which is the case when the entire set E is contained in a line. So I claim that that is the simplest manifestation of this Hart-Lefschetz phenomenon, whatever Hart-Lefschetz is. This is the Hart-Lefschetz theorem staring at you. Of course, you can play the same game not only in plane but in space and also in higher dimensions. So let me translate everything into the language of linear algebra. So I'll start afresh and start with a vector space V. And let me give D for the dimension of the vector space V. V can be defined over whatever field you like. And I'm going to pick a finite subset of vectors. So E will going to be a finite spanning subset of V. This assumption that E should be spanning is there to exclude this one exception. And I'm going to introduce another finite set L, which is the collection of all subspaces of V spanned by subsets of E. So in the previous examples, where you're projectivizing three-dimensional vector spaces and finite subset of vectors in it, L consists of points you see in the picture and also the lines you see in the picture, and also the entire vector space V and the zero subspace. So this L is not just any finite set, but it is a set equipped with an obvious structure of incidences. So points can be included in a line and so on. So let me write L into a disjoint union of LP. Let's say, let me give LK, where K varies from 0 to D, dimension of the vector space D, where LK is the collection of subspaces, again spanned by a subset of E that has dimension K. So this L is naturally what combinatorial is called poset. So it's a finite set, and there are certain relations between them, and so on. So people have tried to generalize the theorem of De Broglie and Erdős to this higher dimensional situation. What can you say about the number or the cardinality of LK, say in terms of E? Oh. And one of them survived in the name of the Dowling-Wilson conjecture. Proposed in the 70s, and it says that for every index K, which is at most half of the dimension D, you must have this inequality. The size of LK, or the number of K-dimensional subspaces in my collection, should be at most the size of L to the D minus K, or the number of co-dimension K subspaces in my collection. So the case of De Broglie and Erdős is when D is equal to 3 and K is equal to 1, where you look at two-dimensional projective planes, spaces, and you compare the number of points and the number of lines produced by them. So this is Hodge-Lefschetz theorem in a weak form.
The conjecture or the theorem? Now I'm confused.
It's a conjecture,
yeah.
And I'm going to show you a theorem. So this is the main result of my joint work with Botong Wang. And what we can show using one of the usual Hodge-Lefschetz theorems, we can prove the following. So for every K, which is at most D half, there is an injective map from the set LK to the set L to the D minus K that respect incidences. So this injectivity assertion implies the numerical equality. But this additional property that's produced, that's just supposed to be satisfied, this injective map between these two finite sets, is one of the main features what qualifies, makes me the right to call this the Hodge-Lefschetz property. So let me try to illustrate this extra feature. So, of course, if you don't have this, then the existence of injective map from here to here is same as the numerical claim. But this is not just any finite set. The two finite sets are related by relations the containment between subspaces. So for example, if this is Lk and this is L to the d minus k with 3 elements and 3 elements, and if you have relations of this form, then you can easily convince yourself that there is exactly 2 different maps which satisfies injectivity and this structure preserving things. So once you shoot one of the bottom elements to the top elements, either to this element or the middle one, then the other, this structure preserving property forces you to produce what your injective map should be. So maps of this form are called matching in combinatorics.
So when you say that respect incidences, what you mean is the imaging.
Yes.
Superspace.
Yes, that's right. I'm only going to map a k-dimensional space to a d minus k-dimensional space that's containing. So there are exactly 2 matchings. But even if, numerically speaking, there is no obstruction to produce an injective map between this finite set and that finite set, there can be some structural obstruction for doing this. So if you have a relation of this form, then there is no injective map from the bottom 3 elements to the top 3 elements. There are 0 matchings between.
And this is true for any field?
Any field, yeah. So maybe that's my first challenge. So I don't know a simple proof of this linear algebra statement. I mean, you should agree that this is a linear algebra statement. Oh. So can you give a simple proof, whatever simple means? Simple in any sense. So my proof with Botung uses what is called the decomposition theorem package for L-adic perverse sheaves. And that is not simple in whatever sense of the word.
Was there any special case known, like some field?
It was known for k equals 1, comparing number of points and the number of hyperplanes. That was a theorem of Motzkin, who worked over them. That had an elementary proof, which works only over real numbers.
Sorry, whose theorem was this?
Whose
theorem was this?
Me and Botung
Oh,
Wang.
the other one, k equals 1.
K equals 1, that's Motzkin.
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 So I call the Hodge-Riemann.
Well, I call it hard Lefschetz because I use one of the hard Lefschetz theorems out there to prove this. And in many respects, this is really a combinatorial shadow of the hard Lefschetz theorem. So I regard this as a linear algebra version of the hard Lefschetz theorem. And just like the usual, whatever hard Lefschetz theorem, in the course of the proof, I produce one injective map from here to here. And there is no God-given one, just like in the usual geometric situation. There may be many, many different choices for the Lefschetz operator, going from degree k to co-degree k. But somehow you should produce in a fuzzy way. And these Lefschetz operators comes in a family, although in discrete way in this case. Okay, so that was hard Lefschetz, and I told you about the hard Lefschetz theorem because in order to talk about the Hodge-Riemann relation, which is in many senses more interesting. So in one version of this hard Lefschetz Hodge-Riemann package, there is the usual classical complex geometry one, where they are really known and they are theorems. But the statement that I'm really interested in, many other people in algebraic geometry are interested in, is the corresponding statement for algebraic varieties. So you can cook up a certain cohomology-like theory only using algebraic variety and algebraic subvarieties. And it's conjectured that such an object also satisfies the analog of Hart-Lefschetz theorem and the Hodge-Riemann relations. But these properties are only conjectured and currently not known. And what I'm hoping to achieve is to at least provide a good testing ground, say at the linear algebra level, to see whether these proposed conjectures of Grothendieck are reasonable or not. So in that setting, Hart-Lefschetz is known. But the Hodge-Riemann relation is not known at the moment for the projective varieties defined over finite fields. So if you're interested in that case, you should think of objects like L coming from a vector space configuration defined over a vector space over a finite field. So I'm going to start telling you the combinatorial shadow of the Hodge-Riemann relation. So for that, let me tell you what a matroid is. So matroid is a certain finite combinatorial object that is very useful in expressing the properties of something like L. There's the definition that I'll choose. And the matroid M on a finite set E is a collection of subsets that I'm going to write by script B. A collection of subsets of the given ground set E, which will play the same role as in the previous part of the talk, which satisfies the following property. The property I want for my collection B is that for any two subsets, B1, B2, in my collection, script B, called basis of my matroid, and for any element x1 in B1 but not in B2, I want there to be an element x2 inside B2 but not in B1, such that if I replace x1 from B1 by x2, then it is again a basis. So this is a combinatorial abstraction of the basis exchange property that you heard from the linear algebra. Whenever I have two distinct bases, then there is a way that there is a certain exchange I can perform to make the basis B1 more like the other basis B2.
And E is not empty.
That's right. Non-empty collection. So just starting bluntly from this abstract axiom, you notice that it's not so easy to produce non-trivial examples of matroids. You start with some random collection of subsets of E, then you check this property for every pair, and there are simply too many conditions to check. So here are some key families of matroids that you should keep in mind. And maybe the most intuitive one is that you start from a connected graph. And you take E, the finite set E, to be the set of edges of E, of the graph. And if you take the script B, the collection of bases of your matroid, to be the collection of spanning trees of your graph, then you can check that this collection satisfies the exchange property that's stated. So that's one class of matroid. Out of any graph, you can construct a matroid.
Spanning trees means the maximum tree in.
Yes. And the second family, that's most interesting to geometers, maybe where you start from a vector space, as before, over some field, and you take E to be a spanning subset of V, and where you take this collection of bases to be the set of bases of V contained in E. Let's say finite. Let's say. And then you check using linear algebra that this property is satisfied, and you get a matroid. And the third class of matroids consists of all matroids not of type 1, 2. So this is the classification of all matroids. And in fact, the class 1 is a subset of the class 2.
Is it clear that class 3 is not empty?
Let's say E is non-empty finite subset. Huh? 3.
It's not empty.
3 is not empty, much more than that. So it was recently shown that if you enumerate all matroids according to their size, then the class 3 consists of 100% of all matroids. So from this combinatorial perspective, what algebraic geometry covers is really 0%. But in that 0%, there is a whole lot of variation depending on which field you're using to define your vector space. So certain matroids can be realized in this form too, depending on what your field is. For example, in the picture that used to be here, the picture of the Fano plane, that defines a matroid that can be only realized over a field of characteristic 2 and not over any other field of different characteristic. So let me define one matrix out of a matroid. So if I have a matroid M on say E, which for convenience labeled by 1 to ... n, I'm going to define an n by n matrix, let's say B of a M, using the following rule. So ij entry of my n by n matrix, so the columns and rows are both labeled by elements of my ground set E, will be 0 if I equals j. So all diagonals are 0, and non-diagonals are little bij if I is not equal to j, where this little bij is the number of bases of my matroid M containing I and So it's a symmetric n by n matrix, and there is one for every matroid.
The basis means the elements of
Elements of the script B. Yeah. So in the category 1, I'm counting spanning trees containing 2 given edges. And in category 2, I'm really counting the vector space spaces containing 2 given vectors I and j for every pair I and j. And I'm going to use that symmetric matrix to formulate one small piece of the combinatorial Hodge-Riemann relation. So again with Boton Wang. What we can prove is that for any matroid M, this matrix Bm is either 0 or has exactly 1 positive eigenvalue. And I think that this is the correct formulation of the first piece of the Hodge-Riemann relation. And there will going to be other Hodge-Riemann relations that I could not formulate succinctly at the moment. And this other Hodge-Riemann relations may or may not be true.
And this has nothing to do with the field. Right?
This has nothing to do with the field. It's a combinatorial statement. So just to have some feeling, let's run one example for this statement. So let's say my matroid M is coming from a complete graph on 4 vertices. So that's my matroid, and bases are spanning trees. There are many of them. And my ground set has 6 elements because there are 6 edges. So my matrix Bm will be 6 by 6 symmetric matrix. There will be zeros on the diagonal, 6 zeros. And the non-diagonals will count the number of spanning trees containing 2 given edges. That number will depend on whether the 2 given edges are disjoint or connected to each other. And the numbers will be either 3 or 4. So the matrix in question will be something like this. Lots of 3s and sometimes 4. And that's our matrix. For every edge, there is exactly one edge that's disjoint from it. And that is the entry 4 here. Same for here, 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 here. And the eigenvalues are, if you ask your computer or someone else, then it will tell you that the eigenvalues are 16, minus 2, minus 2, minus 4, minus 4, minus 4. And this 16 is the unique positive eigenvalue I'm talking about.
So you're saying that the Bm is either 0, so the matrix itself is a 0 matrix?
Yeah, I mean, this is here just to exclude trivial case where the rank of M is 1.
1 or 0. Right?
Yeah, 1 or 0. So again, I don't know a simple proof of this fact. Although the current proof uses no algebraic geometry. The current proof is elementary, but not simple, not short at least. So if you can see a way to prove this, I would like to know. Okay. So what about negative correlation? So I put this in the title. And classically, one of the maybe most famous example of this in combinatorial subject considers again a finite connected graph. And you consider a random spanning tree. Of your graph. And the phenomenon of negative correlation in this context of random spanning trees states that for any two distinct edges,
What is a random spanning tree?
let's say you consider the collection of all spanning trees. So forget about random. So I'm going to consider a collection of all spanning trees, and for distinct edges I and j, you consider the probability that this random spanning tree containing the first edge I, and you compare it to the probability that the random spanning tree contains the edge I, provided that it contains the other edge j. And it is a fact that the first probability is always at least as large as the second probability. So in other words, the events that t containing I and t containing j are negatively correlated. Containing one makes it less plausible to contain the other edge. Yes, let's say everything is finite. So in other words, the assertion is that the following numerical inequality holds. Where Bi is the number of spanning trees containing I, B is the total number of spanning trees, and Bij is the number of spanning trees containing both I and j, and Bj is the number of spanning trees containing the edge j. There's a known principle in matroid theory, maybe going back to Tutt, which says that whenever you have a statement in graph theory that does not mention vertices and only mention edges and spanning trees and things like that, then the same statement should be true for all matroids. And certainly you can ask the same question for any matroid and not just the ones coming from graph. You ask for a given matroid, if you list all its spaces, then does the corresponding statement true? For any pair of elements in the base set E, the probability that the randomly chosen bases containing the first element and the second element, how are they correlated?
So I don't understand why you call this negative correlation.
Because containing j makes containing I less likely. So people have asked the matroid version of the same question long time ago, whether the same hold for more generally for all matroids. And people have discovered that the answer is yes, if M is realizable over all field. So these are called the regular matroids. But in general, again in the 70s, Paul Seymour and Dominic Welsh found a matroid realizable over a field with two elements with this ratio b times bij divided by bi times bj is slightly larger than 1.02 something for some I and j. So explicitly, they found 8 vectors in a 4-dimensional vector space defined over a field with 2 elements and 2 vectors in this configuration, which are positively correlated from the point of view of basis. And amazingly, this example seems to be the only example of this type in the list of first 100,000 matroids. I don't know how they found it, but there are such examples of strange positive correlation. I mean, because the answer is yes for matroids realizable over all fields, if you start with one of your favorite or typical vector configurations, you will not see this positive correlation phenomenon. Usually, if you start with a vector configuration, then the vectors tend to repel each other from the point of view of a basis. But sometimes, if you pick your configuration very carefully, sometimes vectors do tend to attract each other from the point of view of basis.
So how many elements did you say this has? 8 elements?
8 elements, 4 dimension. So why am I saying this? It turns out that what I call the first piece of the Hodge-Riemann relation, the assertion on the signature of this symmetric matrix Bm, has something to do with this ratio, b times bij divided by bi times bj. So if I look at this matrix Bm as a bilinear pairing from all n times all n to all, where all n is equipped with the distinguished basis coming from my ground set E, then I can restrict this pairing to the 3-dimensional subspace spanned by EI, EJ, and sum of all the EIs. These are my elements of the distinguished basis coming from the ground set of the matrix. And then I'll get the 3x3 matrix. Symmetric matrix labeled by I and j. Let's say bij over m. But because I know something about the signature of the Bm, I know something about the signature of this 3x3 matrix. So if I apply Cauchy interlacing to go from Bm to Bijm, I can show that this Bijm has the same property. So Bijm is either 0 or has exactly one positive eigenvalue. Therefore, I can conclude that the determinant of this 3 by 3 matrix should be non-negative. But this is a 3 by 3 matrix that I can explicitly write down the entries in terms of this little bij's. That's a simple exercise, and I can just write down the determinant. So let's pretend that we all did this exercise. And let me rewrite the same inequality in the following way. It says that this ratio of interest, B times Bij, divided by Bi times Bj, multiplied by something almost 1. Rank of M is the cardinality of any basis, is bounded by 2. Therefore, for any M, this ratio is strictly less than 2. So vectors cannot be too positively correlated. There is a universal upper bound on the degree of the positive correlation. Although sometimes this ratio can go above 1. No matter how large your vector configuration is, this ratio should be always bounded above by 2.
The importance of your previous result about the one positive eigenvalue implies this determinant of 3 by 3 matrix is positive. That's
I don't know. If this result is important, then that would make that important. But maybe this is not important.
The significance of the existence of one positive eigenvalue. That gives you this signature.
Yes, yes, yes.
And then you say signature gives you.
Yes, that's right. Yeah. Yeah. I mean, to me, what makes questions like this interesting is that it appears that this ratio, the behavior of this ratio, seems to depend very much on the field. Although I do not know this as a fact. It seems that finite fields tend to produce configurations with very high ratios. Not very high, but at least higher than 1. So let me pose as a question. How large can this ratio be for a given field? So if you fix a field and consider all possible vector configurations in all dimensions and take the supremum of this ratio for all possible choices of I and j, you will get a well-defined real number, which is at most 2, and which is larger than 1, at least for this field with 2 elements. So you get a well-defined invariant of a field. And it appears that this invariant is larger for finite fields or fields with characteristic p than the field with characteristic 0. And this may be a small evidence that the behavior of the higher Hodge-Riemann relations that we have not discussed behave differently in the characteristic 0 situation and the characteristic p situation. I'll stop here.